So we've been talking chapter 2 still. And we got into obviously a bunch of stuff that's related to each other. Obviously, we were talking about quantum numbers. We talked about, obviously, that kind of goes with that electron configuration. And also orbital diagram. So really, again, the quantum numbers basically are sort of the reasoning behind, what orbitals we have present and which orbitals on which energy level. Electron configuration, as we talked about, is the order in which electrons go into the atom. We always write it based on filling order, which is lowest energy levels to highest. An orbital diagram is sort of a visual display, right, of electron configuration, where you can use boxes or lines and arrows to represent the electrons. We talked about a couple of exceptions when we got into the transition metal region. Remember, on the periodic table, there are certain sort of sections, if you will, that go with electron configuration. We have kind of our first two groups there, and that's our S block, which again, S can hold 2 electrons. From 3 through 8 on this side here, 3, 4, 5, 6, 7, and 8. That's our P block, and there's 6 of those spots. Our D block is over here in our transition metal region between those. And lastly, on the sort of bottom part there, those couple of rows, is our F block, right? Now, when we're talking about transition metals, there are actually a lot of exceptions to sort of the electron configuration that you would get if you followed our order. And the 2 that, again, you are responsible for is chromium, which is 24, and copper, which is 29. So again, if we wrote the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 is what you would get if you, again, sort of follow the zigzag sort of order that we talked about. Remember, this is one of those exceptions, and the exception is, again, that we kind of have one extra electron up there in the d orbital and one less in the s orbital. Also, we also talked about shorthand, if you will. So remember that up to here is about 18 electrons, and that is argon's configuration, and it would be 4s1, 3d5 is the correct electron configuration there for chromium. Copper has pretty much the identical sort of exception, and copper is argon 4s1, 3d10. Once again, they're able to do that because really they are very close in energy, those orbitals, the 4s and the 3d, in terms of energy. And so it doesn't take a lot for them to kind of move up an energy level. Now, when we talk about transition metals, and actually, if you kind of, again, look on the periodic table where chromium and copper are, and you kind of go down and kind of in, there is, again, a lot of sort of exceptions in that area on the periodic table. We talked about PD, silver, and so forth. Again, you should just recognize that those are exceptions. If you write for this class the electron configuration following the chart thing that we learned, for those guys, it will not be marked wrong, but just understand that there actually are exceptions. But you do need to write correctly chromium and copper. Again, those are the 2 that you should know. Any questions on any of that there? All right, so we talked about electron configuration, we talked about orbital diagram and quantum numbers. We also want to talk a little bit about ions and what happens when things basically make ions and how that affects electron configuration. So, for example, if I took something like magnesium, who has 12 electrons in his neutral state, a little 1s2, 2s2, 2p6, 3s2. Now, when magnesium gains a charge, it actually will be magnesium with a +2 charge. And we talked a little bit about cations and anions. That is a cation, which basically means that it has lost electrons. And instead of 12 electrons in this case, it actually will have 10 electrons. And that is how it gets the positive 2 charge, because it's got 2 extra protons and electrons to balance it out, right? So because of those 2 extra protons and knowing 10 electrons, it ends up with a positive 2 charge from the protons that are there. That does affect the electron configuration. So if you're writing electron configuration for something that's an ion, you do have to adjust it, and that'll be 1s2, 2s2, 2p6 would be its electron configuration. If we look at something like nitrogen, which is 7, again with no charge, it would be 1s2, 2s2, and 2p3 in this case. Nitrogen, when it does make a charge, will be a -3, and the minus means it's an anion, and basically it has gained electrons. That is why it is overall negatively charged, because it has more electrons than protons, so it has more negative guys than positive guys, and that's going to leave you a net negative charge. So instead of 7 electrons, in this case, actually has gained the number of the charge, which is 3, and it has 10 electrons, and that would be electron configuration for 1s2, 2s2, 2p6. This electron configuration and this electron configuration is the same. They're both 10 electrons, and on the periodic table, number 10 is our friend neon's configuration. Yeah, so it's neon's configuration. So all 3 of those things, neon, magnesium with a +2 charge, nitrogen with a -3 charge, they all have the same electron configuration. And when things have the same electron configuration, that is what is known as being isoelectronic with each other. So something's isoelectronic, it means it has the same electron configuration as something else. The other important thing about that, and we'll touch upon it really in the next chapter as well, is if we think about what happens if we just kind of look at the periodic table per se, we have our neon right about there, and we have our nitrogen before, and then obviously we have our magnesium after. So this is a really important thing because it really is the basis, as we'll talk about, for all bonding. And when things gain charges, that's ionic bonding that's happening. And what happens is magnesium, for example, by losing those 2 electrons, backs up to neon's configuration. And nitrogen, by gaining those 3 electrons, moves forward to neon's configuration. Neon is a noble gas. And one of the things about a noble gas is they are very, very stable. And that is ultimately the goal of all bonding, is for everybody to be really, really stable. And they really want to end up with the same electron configuration as a noble gas. So how representative elements like magnesium and nitrogen do that is they either gain or lose electrons in an ionic compound situation to either move forward if they're a nonmetal to the noble gas that comes after them, or if they are a metal, they will lose electrons and back it up to the noble gas that came right before them, and that's going to create a really stable situation. Now, does nitrogen, for example, or magnesium, does it become neon in this case? It does not. It just has the same electron configuration as neon. It is still nitrogen and it is still magnesium, because out of protons, electrons, and neutrons, which one is most important in terms of what element it is? It is the number of protons, right? The atomic number. So when somebody gains or loses electrons, you don't touch the protons, so they are still that element. They just now have a better electron arrangement, if you will, very similar to a noble gas. And noble gases are super stable, and that ultimately is the goal of all bonding, as we'll talk about, is to reach that noble gas configuration, both ionic bonding and covalent bonding, where they share electrons to achieve that. Any questions on that there? Now, let's talk a little bit about transition metals, and transition metals are a little bit different. Now, transition metals, when they gain a charge, and then when they become ions, some different things occur with them. So, for example, as we talked about when the electrons fill into the atom or get filled into the atom, the 4s orbital, for example, is lower in energy than the 3d subshell. And that means that when those electrons come in, they will fill as we normally do our 4s first, and then obviously they will start filling the d orbitals. Now, what actually happens once you start putting some electrons into those d orbitals is you actually get a switch in the energy of these orbitals. And what ends up happening is the 4s orbital actually ends up being higher in energy than the 3d orbital or orbitals. And that's important because typically, for example, with bonding, any type of bonding, it is the valence electrons that are involved, and those are the highest energy level electrons. So when a transition metal actually goes and loses electrons, and because they're metals, they will make a positive charge, they will always dump out the 4s first, or in this case, are the s electrons first. Could be the 5s or so forth, but the 4s in this example here. And then, if necessary, they can then delve into basically the d orbitals if they need to. And that doesn't happen with representative elements that are outside of the transition metal region. Just those transition metal regions typically will do that. Now, so for example, if we took iron, which is 26, I believe, and we write the electron configuration again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Again, you could also simplify it. That is argon through here, 4s2, 3d6. So, for example, when something like iron makes a +2 charge, which is a very common charge for it, it has basically lost 2 electrons. That's what the +2 means. The plus means it lost electrons. 2 means it's how many it lost. When it goes to do that, it will now end up with 24 electrons rather than 26. And what will happen here is it is going to take out these electrons right here first. So we had 3d6. So if I did this, this is essentially what it looks like at the end there. So it will take out these guys first, and that will leave us an electron configuration of argon 3d6 is left over. Again, the 4s is going to go first because once you fill those d orbitals, it's actually higher in energy than the d's. And again, that happens for all transition metals on all those sort of periods of the transition metals. Now, let's say we had iron with a +3 charge. That means iron in this case would have 23 electrons. It once again will take out those 2 from the s. At this point, the next highest is the d. It will climb over there to the d and take out 1 from the d. And now you will actually end up with argon 3d5. Yeah. There's so many questions on that. This is why you might have seen, or you might see occasionally, people will write electron configuration like all in order, and all the 3s together, all the 4s together, and so forth. And it's because of this situation that occurs, and that's really electron configuration based on energy rather than filling order. But pretty much all chemistry classes, including this one, you should write it based on filling order like we learned, where the S's get the electrons first and then the D's. I only taken one class in my entire life that we did the other way. Yes. It's all for all transition metals. Specifically, the 4s is for the first row transition metals. It actually happens when you start filling the 3D, and that will basically happen when you get to the transition metals. Transition metals are pretty much where the d orbitals start. So before that, you don't have to worry about because there's nothing in the d. So it will do that, and but as soon as you just hit at the very first transition metal, which is Sc over there, you're going to start putting some electrons in the d orbitals, and that's when it'll occur. Y- Yes, so with non-transition metals, which are sometimes referred to as representative elements in terms of metals, which is like group one and group two and aluminum, basically it's the ones at the very end of your electron configuration are always the ones they lose. It's the valence electrons, basically, right? And that's what they lose. So for when we did magnesium back here, this was the two valence electrons for magnesium, which is the highest energy level, and thus the one he's going to lose, right? And by the way, that's that they gain the electrons in there as well. But we're talking about losing. But here, when we talk about transition metals and valence electrons, which are those highest energy level, they can have upwards of like 12 because of this situation, all the electrons in here are technically considered for transition metals valence electrons. Although a lot of times people call it just two because they always kind of take the S first, but you do have to dig into the D sometimes. And that's why when we talk about valence electrons and the periodic table there, um, when we get to the transition metals, which are here, we roll with kind of the 1 through 18 numbering. So we go 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll make my transition metal region bigger. But we go with the regular sort of numbering, and technically that is the number of valence electrons it has. So if you look at iron up there, it technically is in group 8. And iron's valence electrons are these guys right here. So that is what iron has available to it. Will they ever lose them all? No, because you'll never see like an iron with a +8 charge. Or, for example, if you get to zinc, which is number 12 up there, has 12 technically valence electrons, you'll never see a zinc with like a +12 charge because they won't lose it. So when we get to those transition metals, because as soon as you get into there, has to fill a d orbital, that's when you see the switch occur. And it doesn't happen for those other ones. Other questions? Now, another sort of result of this is unlike the representative elements like in group one and group two and even group three, the transition metals do not end up in noble gas configuration because, again, in order for something, for example, like zinc to get back there, he's got to dump out 12 electrons, and it's just not going to happen. So transition metals don't typically, when they lose electrons, end up in a noble gas configuration. They end up typically with some incompletely filled d orbitals, usually is what they sort of end up with. By the way, for our exceptions like chromium and copper, again, if you had copper with a +2 charge, because copper's electron configuration, right, is argon 4s1 3d10, if it was to become copper with a +2, he only actually has one s electron to lose, right? So he would then have to take three out of the, or not three, one more out of the d orbital there. So it works the same way. You just got to be careful with those couple of exceptions that we are responsible for here. But you may also see some of those on those ones that are actually exceptions below it as well. Question on that there. So why don't you write some electron configuration for the following? Why don't you do, let's do calcium. Let's do sulfide. Let's do Mn4 plus. Let's do nickel 2 plus. All right. So in case you can't see, calcium is 20. Sulfur is 16. Mn there is 25. And nickel is then there 30, 20, 28. Okay, let's take a look, see how you're doing. So we'll start with calcium here, and we'll see calcium with no charge, which would be 20. So that would be a little argon, right? 4s2 in this case. Or again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Obviously here, calcium with +2 charge means it has lost 2 electrons. So that's going to drop it to 18 electrons. Once again here, these are the 2 valence electrons in calcium. and those are the two that are going to get lost. That's going to leave us pretty much this configuration right there, which is basically argon's configuration. So calcium in this case, by losing 2 electrons, will drop backwards on the periodic table there to the noble gas that came right before him, which would be argon. Any questions on that one there? Coming to our sulfur with no charge, 1s2, 2s2, 2p6, 3s2, and 3p4 in this case. By the way, if you want just shorthanded, you have to go back to neon in this case. And again, write the rest of it there. In this case here, -2 means that it has gained 2 electrons. So again, instead of 16, it will have 18, much like this guy over there. Bad choice, I suppose, on my part. Those 2 electrons, by the way, are going to come into our p subshell here, which has room for them, right? Because they could hold 6. So they're going to grab onto those 2. And that is then going to give us 1s2, 2s2, 2p6, 3s2, 3p6. That also is 18, which is argon's configuration. So again, here sulfur going forward on the periodic table by accepting those 2 electrons and reaching that noble gas configuration. Any questions on those 2? Now to our transition metals here, we got Mn, which again is, go all the way out there, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5 in this case. Once again, that being argon, 4s2, 3d5. This right here is the 7 valence electrons for manganese, group number 7 there on the periodic table for Mn. Again, the number of valence electrons equals the group number. And again, when you're doing the transition metals, you got to do the 1 through 18 numbering for that center part there. Here, what we have our transition metals is losing 4 electrons. So it needs to lose 2 out of here first. So those definitely are going. We still need 2 more electrons. And the next highest after that will be our D. And we'll take 2 out of there. That should leave us for our guy with the charge. 3 should be left over at that point, right? Any questions on that one there? Okay, looking at nickel, which is 28, and nickel with no charge, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 1, 2, 3, 4, 5, 6, 7, 8. Sounds good. 3d8. Again, that's argon in front of it there. So we got a little, I'll go up on top here. Argon 4s2, 3d8 in this case, yes. This here would be technically the valence electrons for nickel. And there's a lot of sun in that direction, but I think it's a number 10 over there, which would be those 10 electrons in the 4s and the 3d as well. Nickel here with a +2 means in this case, it actually only needs to drop, again, its s's first. And again, that's what happens here in our D, our transition metals, leaving us argon 3d8, which would be there. So when it becomes nickel with a +2 charge, it has basically 8 d electrons hanging out. Any questions on how to write electron configuration for things with charges, both transition metals and representative elements? Yeah. Again, as you can see here, representative elements are much easier. You kind of just play with the last thing in your electron configuration. The transition metals, you got to remember, you got to go S first and then D. And by the way, that does work the same way. If you drop below, for example, on the second period of transition metals, where you got like silver and MO and all that, they will lose the 5s electrons first and then come into the Ds. So it works kind of the same way for all the transition metals. Any questions on that there? Yeah. Then let us talk about the actual periodic table here. So the periodic table, we have groups and we have periods. So a reminder that I think we touched upon it the other day. Groups go up and down. Periods on the periodic table go kind of left to right. There are a bunch of numbering for the groups as we've been talking about. Again, on a lot of periodic tables, there's sometimes the A numbering, there's also sometimes the B numbering, and there's also just a straight 1 through 18 type numbering. Pretty much most chemistry classes that you take, we again use the representative numbering, which is the A numbering. And for the A numbering, once again, for group 1, it is here. By the way, add a note. Group 1 starts with lithium and not hydrogen, and we'll talk why that is, but it actually starts with lithium, even though hydrogen is hanging out there. Group 2 is here. We skip the middle, which is our transition metals. We go to group 3, group 4, group 5, group 6, group 7, and group 8. So when we talk about group 1, 2, 3, 4, 5, 6, 8, those are the locations of where we're at. Like I said, probably previously, most people really don't like a 1A, 2A. They just kind of do 1, 2. Most people are using the A numbering anyways, and that is what we will use here as well. Periods, there are actually 7 periods on the periodic table. Again, going left to right, 1, 2, 3, 4, 5, 6, 7, as we talked about when we were doing electron configuration. Those are essentially the energy levels, yeah? Those are the N values, right, that go 1 through 7. So kind of convenient. This goes 1 through 7. Again, you could count off the electron configuration on the periodic table like we talked about. And those periods basically represent, in a sense, the energy levels as you go through there. All right, so let's talk about it here. The periodic table has our groups, it has our periods. As we also talked about on most periodic tables, above the symbol is the atomic number. And we remember, hopefully, the atomic number, right, is our number of protons, right? Also sometimes abbreviated as a Z, right, for atomic number. Number of protons and atomic number, as we talked about, really important because, again, every single element has its own atomic number, which means it has its own number of protons. And that is really the one of the 3 subatomic particles that's most important in terms of what element you're talking about. Now, it's also broken up into 3 categories. There are metals, nonmetals, and metalloids. On most periodic tables, even up there, somebody got a big pin out, it looks like maybe. You can see what is sometimes referred to as a staircase that kind of starts around boron and works its way down. And for example, here, right, kind of working this way. And to the left of the staircase there, that is where we find metals. By the way, the ones on the bottom are also metals. And those guys on the bottom are metals because technically if you follow the numbering, these guys, again, should actually go right in there with all the other metals, the transition metals. So those guys actually go in that location. Those 2 are on the bottom. To the upper right there of our metalloids are our nonmetals, and on the staircase there are our metalloids. Some books might throw boron in there, but a lot of books will just consider it a nonmetal as well. So a metal is a good conductor of heat and electricity. Metals are also malleable. You can hammer into sheets, you can pull them into wires. Metals typically have very shiny appearances. Pretty much all metals are going to be solids at room temperature, except for our friend mercury, which on a lot of periodic tables is blue for that reason. And that is a liquid on the periodic table. This is also why, right, as I mentioned a second ago, when we come to our group 1, who is this guy right here? That's hydrogen, right? And hydrogen is what type of element? It is a non-metal, even though it's hanging out over there. And that is why it is not part of group 1, which are all metals. So even though it's kind of hanging out over there with group 1, hydrogen is a non-metal. It's hanging out with group 1 because it shares a lot of similar properties with how group 1s behave, especially in terms of acids and when it's an aqueous solution. So again, they oftentimes will put hydrogen over there If you're old like me, years ago, periodic tables would actually throw hydrogen like on both sides. You actually see it sometimes on both sides listed, but they don't do that these days anymore. So they kind of just keep it over there. Now, non-metals, on the other hand, do you have a question? Yeah, yeah, yeah. Why do we put hydrogen on that side? On the right? Yeah, it would in the sense of it's a non-metal, but as we'll go through some different chapters, hydrogen behaves in a lot of cases, and sometimes when it's in aqueous solution, like in acids, which is the main thing that makes up an acid is a hydrogen H plus. It behaves a lot in aqueous solutions like group 1 metals, and we almost treat it a lot of times when we name things and think about how it's working in an aqueous environment, very much like group 1. So that's why they kind of put it over there. Because it is a non-metal, it actually should be technically on the right-hand side, but because it has a lot of very similar properties, and obviously the periodic table is put together to put things that have similar kind of characteristics and properties, since it a lot of times has this very similar sort of characteristics, it's over there. So for example, when we do like naming, when we name non-metals, we name it a certain way. But when we have hydrogen involved, we actually kind of name it almost like we name the metals and stuff like that. So it has a lot of similar sort of characteristics, and that's why it's over there. Yeah. All right, so non-metals on their head, like I said, is upper right, except for hydrogens on the left. Non-metals are a little bit different than metals. They have kind of the opposite characteristics. They're poor conductors of heat and electricity. They also have a more, they're dull and brittle as well. They have a more variety of states, if you will. Some non-metals are gases, some are liquids, some are solids, as opposed to metals, which are mostly solid. And I would say pretty much all of our diatomic molecules that are elements are nonmetals. Those are our hydrogens, remember? Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Remember, these are all elements. And the way that they come is diatomic molecules. And most of those are gases, like up through here are pretty much gases. And then these guys, like you can see there, are kind of a liquid with a vapor over it, and uh, some also a liquid for iodine as well. Now, up on the staircase there, they are considered semi-metals, if you're old, or nowadays they call them metalloids a lot. And what semi-metals have are properties that fall really on either side of where they're located. The same metalloid could have some properties that would be considered more of a metal property, and the same metalloid would have some properties that are kind of more considered more like a gas property. And it makes sense in the sense of where they're located, because as you go from metals to non-metals, those are kind of the guys that bridge most of the metals to the non-metals. So they do have some characteristics that fall on both sides. Like I said, some books will include boron in that, and most of the time we do treat boron more like a non-metal, but sometimes they will kind of include that, and that's a staircase coming down. Now, some groups on the periodic table have special names. Group 1 over here, again, as we talked about, starting with lithium, those are the alkali metals. Right next door, group number 2 there is our alkaline earth metals. And group 1 and group 2 on the periodic table is where we find a lot of strong bases basically come from. And that's because, for example, the word alkaline means basic. Yeah. So that's where we can kind of produce a lot of our strong bases like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium, barium. Basically, if you go this way, hang a right and come down and you throw hydroxide on those guys, you have probably a strong base that you just made in that sense. If we come all the way over here to group 7, those are our halogens, and we looked at those in that experiment not too long ago. And that's our fluorine, chlorine, bromine, and iodine. Those guys all come as 2s. And as we talked about and saw, right, reactivity increases in group 7, right, as you go up in that case. And the last sort of group here is group number 8. And group 8 is the noble gases. And noble gases means set apart. Noble gases are what are sometimes referred to as being chemically inert, which means they don't react. They will react with themselves, but not other things. And they're super stable. And that's why we were just talking about a second ago that when things lose and gain electrons, their ultimate goal in bonding, for example, is to get to that electron configuration. That's going to create a really stable situation for bonding to occur. So you do need to know, obviously, where group 1, group 2, 7, and 8, and all the groups are located, and the names of those groups. Now, a couple other things, obviously, as we were talking about here, between group 2 and 3 on the periodic table, these are our transition metals. And they do have some different characteristics as well, as we'll talk about, including they typically can lose a variable amount of electrons. The bottom 2 rows are set there so that your periodic table is not giant in your book, or if you had a book anymore. But again, if you follow the atomic numbering, they actually should go right about there. And that's the lanthanide and actinide series. Those are the elements they should follow on the periodic table. I only seen one place they ever did that, and they had to put it on a big wall. Took up the whole wall because they shifted everybody to the right to slap those 2 guys where they were supposed to be. So obviously you need to know where transition metals are. And again, these guys are sometimes, as I mentioned, referred to as inner transition metals because technically they should kind of go in that location. Question on the periodic table. So obviously groups, periods, the names of the groups and transition metals located where metals, non-metals, and metalloids are located, and some properties of those things. All right, we're going to finish up here talking about periodic trends, and we're going to add a couple to it, I think. So we got ionization energy. We're going to talk about Z effective, I think. And we'll talk about electronegativity. All right, so let's get into some periodic trends here. The first periodic trend we're going to talk about actually is the one I just skipped, what is referred to as Z effective, and that is the effective nuclear charge. So the effective nuclear charge is the charge that outer electrons, bless you, feel as a result of what is referred to as shielding. So let's just take a very simple example, which is lithium, 1s2, 2s1, right? That's 3 electrons. It has 1 valence electron, which is the outermost electron, that guy. And it has 2 core electrons, which are closer to the nucleus, which would be those 2. And since it's lithium, it has a +3 charge there in the nucleus. And on our first energy level, you know, we have 2 electrons hanging out. I'll just draw it like this for purposes of this illustration. On the second, we have our valence electron hanging out. So remember that opposite attraction there, or electrostatic attraction, increases with increased charge size. And what this means is these core electrons down here will feel the full brunt of the +3 charge from the nucleus. So they're going to be held pretty tightly because they're right up front. They're going to feel the full +3 charge. Now, when we talk about the valence electron, which is out there lonely by himself over there, he actually does not experience the same +3 attraction to the nucleus because what he's experiencing is what is known as shielding. And he is shielded from the nucleus positive charge by the lower energy electrons. They essentially are in his way. An example, right? If you're at the movie theater, you sit down in the middle, got a nice seat, perfect thing of the screen, and right before the movie comes, somebody sits in there with a giant cowboy hat, right? Blocks out pretty much, shields half the screen. That's not so good. I hear they assign seats these days to go to the movies, but it still happens, I suppose. So that's sort of what's happening here. Because we have these lower energy electrons, they're actually shielding it. You can actually calculate the effective nuclear charge that that electron is feeling. You take the +3 charge from the nucleus, from the protons. You take the number of electrons that are shielding, and subtract it. And ultimately, what that valence electron is feeling on the outside is not a really strong +3 attraction to nucleus. It's only feeling like a +1 attraction. And that is one of the reasons why it is being held not as tightly, right? And why valence electrons can kind of go off and do bonding and involved in bonding. And also why core electrons, for example, are held really tightly and why they're never involved in bonding, because they are never going to be released. The general trend on the periodic table when you talk about effective nuclear charge is it increases as you go to the right and up and decreases as you go down. If you just think about it, you go to the right, everybody has a larger atomic number than to the left, which means their nucleus has a greater positive charge. So as you go to the right, the nucleus now has a bigger positive charge. So even those valence electrons, which are way out there, will actually feel a little stronger of an attraction to the nucleus because there's just a lot more protons and positive charge there than there is on the left-hand side of the periodic table, where they don't have as many protons, so it's not going to pull those guys in as much. And that also affects something like size. The next trend is ionization energy. And ionization energy is the energy that is required to remove an electron from the gas phase of an atom. And when we remove an electron or electrons, that is when we make cations. So we think about cation formation when we talk about ionization energy. In general, the general trend for ionization energy, the first ionization energy, is it increases as you go up and to the right and decreases as you go down, the first ionization energy. By the way, electrons actually come off one at a time. They actually do not drop all the electrons off at the same time. So if we take something like magnesium here, the first thing that happens is magnesium will actually lose just one electron and become positively one charge. The energy needed to do that is the first ionization energy. Then what happens is this guy that now has a +1 charge will drop off another electron. And the energy to do that is what is known as the second ionization energy. And lastly, the +2 guy will then drop perhaps another electron and become +3 charge. And that is the third ionization energy. What happens when we look at the trend between the first electron to the second to the third? Is it easier to pop off the first electron or the third? Which one is easier? That requires less energy. The first one, yeah. The first one's neutral. So when you pop off that electron, what happens to the electron density? Shrinks, brings everybody closer to the nucleus, right? So now it's going to be sitting closer to the nucleus and going to be held tighter. So it takes a lot more energy to remove the next one. Remove the next one, everybody shrinks in a little bit more, right? Now I try to remove that third one, it gets even harder, right? Because everybody's closer to the nucleus. By the way, that's why something with a positive charge is actually smaller than the neutral atom, because it loses electron density as it loses electrons. So the general trend is the first ionization energy is smaller than the second, and the second is smaller than the third. It keeps getting harder and harder to remove electrons. When we think about magnesium, perhaps you know, magnesium typically makes what type of charge, by the way? Typically makes a +2 charge only, yeah. And that's because if we look at the electron configuration, 1s2, 2s2, 2p6, we got 10 there, 3s2. These are the two valence electrons, right? These are the core electrons. So when we take off the first one and the second one, it gets harder to do that. But at this point, we are now into core electrons, and good luck on that. That's not going to happen, because you can even see the energy jump here. It goes from like 1400 to almost 7800. You know, it's almost a six-fold sort of jump, 5 to 6-fold jump of energy needed to do that, and it's just not going to happen under normal conditions. And that's why, for example, something like magnesium taps out at +2, because it's lost those two valence electrons, is not energy efficient to try to rip out those core electrons. It just takes too much energy to do so. Any questions on that there? So here's a little table of ionization energy. And again, you can see magnesium as we see here. Big jump. Also, sodium, for example, we see sodium, which is 495 to remove the first electron, and then it goes to 4,500, almost a tenfold jump in energy needed to try to remove the second electron. And that's why sodium is only +1, because when we look at sodium, 1s2, 2s2, 2p6, 3s1, it has only one valence electron. And now you're going to need a heck of a lot of energy to try to rip out that core electron again. Is probably not going to happen. We can even see aluminum here is a +3 as it goes from its third electron at 2,700. It skyrockets to about 11,000 in terms of energy that you need. And at that third electron removed, you're now into this core electron. Again, it's definitely not going to happen.